There's a skyscraper in Tokyo right now, sheathed in glass, catching the afternoon light, looking about as solid and permanent as anything humans have ever built. It is not moving. It will never move. That's the whole point of a building, isn't it? To stay still. Except that's wrong. In a serious earthquake, that tower will sway several feet to one side, then several feet back, swinging through the air like the slow tip of a metronome. And here's the strange part. That motion isn't a failure. It isn't the building straining at its limits. It's the design working exactly as intended. We call these buildings earthquake-proof, but proof, here, doesn't mean what you think. We picture something immovable, a fortress that shrugs off the shaking earth. The truth is almost the opposite. Japan's tallest towers aren't built to resist earthquakes. They're built to move with them. And once you understand why, you can never look at a skyline the same way again. Start with the assumption almost everyone makes. If the ground is going to shake violently, surely you want the strongest, stiffest, most rigid structure possible. Pour more concrete. Add more steel. Make it a bunker that refuses to budge. It sounds obvious. It's also the fastest way to get people killed. A rigid building has nowhere to put the energy of a quake. The ground heaves, the structure resists, and the force has to go somewhere, so it tears through joints and snaps brittle members until something gives. A flexible building does the opposite. It bends. A modern steel skeleton tower is engineered to flex, to lean, to ride the seismic wave the way a tall tree rides the wind. On a normal gusty day, the top of a skyscraper can already drift around 3 feet to each side, and nobody inside notices. That flexibility is a feature, not a flaw. But flexibility solves one problem and quietly creates another. Because once you let a building move, you have to ask the much scarier question: what happens if it starts moving at the wrong rhythm? This is where the real enemy reveals itself, and it isn't raw force at all. It's resonance. Think of pushing a child on a swing. You don't shove harder and harder. You give a small push at exactly the right moment, again and again, timed to the swing's natural rhythm, and those tiny pushes add up into a huge arc. That's resonance. Little inputs, perfectly timed, building into enormous motion. Every structure has a natural rhythm it likes to sway at, and if an earthquake happens to shake the ground at that same rhythm, each pulse adds to the last, and the building's gentle sway can amplify into something violent and self-destructive. Engineers talk about being able to tune a skyscraper the way you'd tune a guitar string, because that's genuinely the physics involved. The danger isn't a single hard punch. It's the earth finding the building's frequency and pushing the swing. So now the goal sharpens. You don't just need a building that bends, you need a building that refuses to fall into step with the quake. And here's the trap. The instinctive fix makes it worse, because the obvious move is still to stiffen things up. But stiffening a building changes its natural rhythm, and it can shove that rhythm straight into the range of frequencies that real earthquakes produce. You can engineer yourself directly into the danger zone while believing you're making the building safer. The answer was never about adding more strength. It was about controlling motion and draining energy. Japan ended up codifying this into 3 layers of defense, and the names matter less than the ideas behind them: strength, damping, and isolation. The first layer is just solid, ductile construction that holds together. Fine. But the clever work happens in the other 2, and this is where the engineering starts to feel almost alive. Damping is the simplest idea. Give the energy somewhere to go. Engineers install dampers throughout a tower. Devices filled with oil or viscous material that work exactly like the shock absorbers in a car. As the building flexes, these dampers stretch and compress, and they convert the motion into heat, bleeding the shaking away before it can build up. The earthquake's energy doesn't get resisted. It gets quietly turned into warmth and lost. Then there's the showpiece, the tuned mass damper. High up near the top of some towers hangs an enormous counterweight. In the famous example over in Taipei, it's a steel sphere weighing 660 tons, suspended like a giant pendulum. When the building sways one way, the weight lags and swings the other way, pulling against the motion and canceling it out, again converting all that swing into heat. The building is essentially carrying its own built-in brake, a pendulum designed to fight the sway in real time. And the most elegant trick of all sits at the very bottom. It's called base isolation, and it borders on cheating. Instead of bolting the tower rigidly to the ground, engineers set the entire building on thick layered pads of rubber, lead, and steel. When an earthquake hits, the ground lurches violently, but those pads flex and absorb the shock, so the building resting on top of them barely moves at all. The earth jerks sideways, and the tower just sort of glides, calmly, almost serenely, while the violence happens underneath it. The energy is intercepted at the foundation before it ever has a chance to climb the structure. It's genuinely brilliant modern engineering. Computers, oil dampers, 100-ton counterweights, laboratory-tested rubber bearings, cutting edge. Except the core idea isn't modern at all. It's roughly 1,400 years old. In Japan, there stands a wooden pagoda at a temple called Horyuji. Its central pillar was cut from a cypress tree, felled in the year 594. This slender wooden tower has stood through more than a millennium in one of the most earthquake-battered places on Earth through countless major quakes, and there is no record of a 5-story pagoda like it ever collapsing in one. Wooden buildings around them have burned and fallen. These towers keep standing. How? And this is the honest part. Even now, experts don't fully agree. What they found is that the survival comes from a combination of features working together, not one magic trick. The floors of the pagoda aren't rigidly bolted into a single stiff column. They're loosely stacked, almost resting on each other, so during a quake, each level can slide a little against the ones above and below. The whole tower wriggling like a snake instead of cracking like a stick. The wide, heavy eaves jutting out from each roof act like a tightrope walker's balancing pole, steadying the sway. Friction in all those loose wooden joints quietly drains energy with every movement. And running up the middle is that central pillar, the Shinbashira, which barely moves while the tower flexes around it. That ancient tower, in other words, was already doing what modern engineers spent the 20th century rediscovering. Don't resist the earthquake, absorb it, scatter it, move with it. And here's where the whole story closes its loop in the most satisfying way possible. When engineers built the Tokyo Skytree, a 634-meter broadcasting tower finished in 2012, they put a system at its core that holds a heavy central column, structurally separated from the main frame, connected through dampers so that the column and the tower sway differently and cancel each other out. They reduced the tower's vibration by roughly half, and they named the system after the pagoda's pillar, the Shinbashira. The newest engineering in the country is a high-tech retelling of an instinct a temple builder had 14 centuries ago. This philosophy didn't stay theoretical either. After a 1981 overhaul of Japan's building standards, a clear dividing line appeared between old construction and new. When the devastating Kobe earthquake struck in 1995, the overwhelming majority of buildings that collapsed were the older ones, built before those modern rules. The buildings designed to move were the ones still standing. So go back to that glass tower in Tokyo, catching the afternoon light, looking perfectly reassuringly still. It isn't still at all, not really. It's poised. Underneath it, rubber pads are waiting to swallow a shock. Inside it, dampers are ready to turn violence into heat. Somewhere up high, a counterweight hangs ready to swing. The whole structure is quietly tuned never to fall into rhythm with the ground. It was never trying to win a fight with the planet. It was built to dance with it, using a lesson a wooden temple figured out 1,000 years before the first skyscraper ever rose. The calmest looking thing on the skyline is hiding the most motion and the most intelligence.